This is calculating the solubility product, or Ksp for AP Chemistry. What I have here is an image of lead 2 chloride in equilibrium with its ions. Now, lead 2 chloride is considered an insoluble compound, but we can see that it is actually dissociating slightly in water. And we can write an equilibrium expression for this, which I have shown right here. Now, notice that we did not include the lead 2 chloride because, if you remember, we omit solids from equilibrium expressions. So here's some equilibrium expressions for various compounds, and notice that they are all very small numbers because these are insoluble compounds. So let's take a look at what this means. So we have Ksp is 1.2 times 10 to the negative fifth for lead 2 chloride. The chloride concentration times the lead concentration is Q. If Q is greater than Ksp, we will see a precipitate. Remember, precipitate means solid. A solid forms. If Q is less than Ksp, then no precipitate forms. So K greater than Ksp, a precipitate forms. Q less than Ksp, no precipitate forms. Let's see if you remember how to write equilibrium expressions. So I want you to write equilibrium expressions for the following reactions. So pause the recording and do so. Let's see how you did. Did you remember that you needed to use the coefficients as exponents? So make sure that you did that. All right, we're going to go on to some calculations now. We're going to be calculating Ksp from molar solubility data, and there will be three different problems. So our first one is we're told that the solubility of aluminum hydroxide in distilled water is 3.7 times 10 to the negative 9th molar. So let's first take a look at our reaction and our stoichiometry. So we have x, x, and 3x. Now we've got an ICE table. We do not include solids in the ICE table. Initially, we have no ions, but that immediately changes. We're told when we're all done that 3.7 times 10 to the negative 9th molar has dissolved. This is a 1-to-1 ratio, which means the concentration of aluminum ions is 3.7 times 10 to the negative 9th. Since this would be a plus x and a plus 3x, that means that we have to have 3 times 3.7 times 10 to the negative 9th molar of the hydroxide ion. If we write our Ksp expression, Ksp is our aluminum concentration multiplied by the hydroxide ion concentration cubed. So we're just going to take the bottom line of our ICE table and fill it in. So we have 3.7 times 10 to the negative 9th. And then we're going to figure out what this value is in the calculator, and that is 1.11 times 10 to the negative 8th. We're going to cube this because we have a coefficient of 3. And when we calculate this, we have about 5.1 times 10 to the negative 33rd. This problem is the same type, just a little more challenging, because instead of giving us the molar concentration, they gave us the number of grams per liter, which means we're going to have to convert grams to mLs. So I've already calculated the molar mass of PbBr2, so PbBr2, the molar mass of that is 367 grams per mole. We will need that. We know that we're going to need our Ksp expression, so let's go ahead and write out what is happening as the lead 2 bromide dissolves. So we'll have the lead ions plus 2 of the bromide ions. So Ksp is going to be equal to our lead ion concentration times our bromide ion concentration squared, because we have that coefficient. All right, let's figure out the concentration of the lead bromide based on our 4.34 grams. So we have 4.34 grams. We're going to divide that by the molar mass, 367 grams per mole. And that tells me that I have 0.0018, there's two ones, 0.1183 moles per liter. That means we've got 0.0, and I've got a boo-boo here, let me fix this. This should be 0.01183, 0.01183 molar. The bromide ion concentration is going to be equal to twice that. So we're going to have 0.02366 molar. The lead concentration, since it is a 1-to-1 ratio, is 0.01183 molar. Now we're ready to just plug things into the Ksp expression. So we have that Ksp is going to be equal to the lead concentration times the bromide concentration squared. Don't forget to square it. And that's going to be 6.61 times 10 to the negative 6th. And there's your answer. This is our last calculation. We have a sample of lead 2 carbonate. We're told at equilibrium the concentration of the lead 2 ions is 2.7 times 10 to the negative 7th. So we're just going to put that right into the ICE table. We have 2.7 times 10 to the negative 7th. I'm going to check the stoichiometry. X, X, and X. So everything's a 1-to-1. We don't worry about the solids in the equilibrium expression, and we could fill all this ICE table in if you wanted. So as we dissolve, we're going to be making a 1-to-1 ratio of the lead ions and carbonate ions, which means our final carbonate ion concentration is also 2.7 times 10 to the negative 7th. And now we just need to write our Ksp expression. We're going to have lead 2 plus times the concentration of the carbonate. And we just plug in our values, so that would be 2.7 times 10 to the negative 7th. And we're going to square. Our final answer is 7.3 times 10 to the negative 14th.